Hello everyone, I am Chen Yuanwu from University of Pennsylvania. Today I'm going to present our paper FlexChain, an elastic disaggregated blockchain. The traditional smart contracts are used to perform data-intensive operations, and as the number of users or size of records increase, these activities spike quickly, which significantly reduces performance. In order to maintain high performance, memory needs to be enlarged to accommodate the working set of transactions. At the same time, a new class of compute-intensive smart contracts are emerging, including refugee identification, medical imaging and diagnosis, carpooling, countermeasure against DDoS attacks in 5G, games, and carbon pricing. These smart contracts more or less perform artificial intelligence on-chain, such as classification and clustering, in order to provide strong security guarantees for their customers. We pick two representative smart contracts and profile their resource utilization while running on Hyperledger Fabric. The first one is a k-means query contract, where each query represents a user submitting a request with a new vector, and the contract finds and returns the nearest cluster from pre-trained clusters. The second one is a YCSB key-value store contract. The k-means query contract incurs 91% average CPU utilization even when clusters are pre-trained, but only incurs 1 gig maximum memory utilization. On the contrary, the YCSB contract incurs 10 gig memory utilization, but only 10% CPU utilization. These results suggest an extreme variation in the utilization of different types of hardware. Thus, permissioned blockchains should be redesigned to scale CPU and memory resources flexibly and independently. Resource disaggregation is an ideal solution to meet such demands. Instead of organizing resources in a unit of monolithic servers, resources of a disaggregated data center are partitioned into physically distinct pools that are dedicated to processing, memory, or storage. The pools are connected by a fast network, for example, RDMA over InfiniBand. Each pool typically contains a small amount of other resources. For example, a modest amount of DRAM will be necessary in the compute pool. As a result of disaggregation, part of what used to be local memory access now becomes remote memory access. This novel infrastructure brings us several benefits. First, it allows independent upgrade and expansion of each resource. If a new processor technology becomes available, or if a compute-intensive smart contract requires additional CPUs, additional compute nodes can be deployed without upgrading memory nodes or worrying about the compatibility between different components. Second, it provides the illusion of a near infinite pool of any resources. Third, disaggregation promotes efficient resource utilization and prevents fragmentation, because different resources are now allocated separately from the corresponding pools. So there's no longer a need for rigidly allocating a VM with a fixed CPU count and memory. FlexChain is a novel blockchain service that leverages recent innovations in resource disaggregation. It is designed for blockchain as a service environment. FlexChain's design is based on several key insights. We observe that the execute order validate, or XOV in short, architecture, as used by Hyperledger Fabric, lends itself naturally to disaggregation. First, the execution phase is fully in parallel. Second, the first part of the validation phase is inherently parallelizable. As a result, we can auto-scale these stages to arbitrary number of CPUs in the compute pool. Third, most of the blockchain states reside in key-value stores, which can be hosted in the memory pool. Similar to generic XOV blockchains, FlexChain operates as a unit of virtual peers, but there are a few differences between them. A virtual peer in FlexChain can run on multiple compute nodes, multiple memory nodes, and multiple storage nodes, and each hardware component can also be provisioned for multiple logical peers. the ordering service node continues to run on traditional monolithic servers. Instead of using a local key value store, FlexChain disaggregates world state using a three-tier architecture that combines compute local memory, and remote storage. In particular, temporary data is kept in local memory because such data is small and unlikely to be reused across transactions. FlexChain consists of a load balancer, a compute pool, a memory pool, a storage pool, and the ordering service nodes. Now let me introduce the lifecycle of a FlexChain transaction. To initiate the transaction, a client sends a message to the load balancer, where P1 represents the virtual peer. The load balancer dispatches the received request to the least loaded compute nodes belonging to P1. Here it is C1. Then C1 performs the execution phase of request by interacting with P1's copy of the world state, which is primarily stored in the remote memory pool. Upon receiving enough endorsements, the client assembles the transaction and submits it to the ordering service. Once the transaction block BI has been generated, ordering service sends the block to every logical peer for validation and commitment. For example, in order to send block BI to P1, OSN send block BI to compute node C4 so that compute node can perform endorsement policy evaluation on the transaction within the block fully in parallel. Once finished, C4 sends a message containing the consequent validity bit mask to the primary compute node. The centralized validation manager on the primary node will finally perform a complete check and world state update. The updated world state will be written into remote memory, and the block itself will be written into remote storage. A permission blockchain system often involves several parties located on multiple data center infrastructures. Now we demonstrate a cross-data center deployment of FlexChain. There can be two potential ways to do so: splitting according to resource type or splitting according to virtual peers. Splitting according to resource type means hosting a compute pool in data center 1, a memory pool in data center 2, and a storage pool in data center 3. This results in a logical peer to be spanned across multiple data centers. So this approach is not realistic, since RDMA cannot be used over a wide area network currently. While a single logical pair cannot span multiple data centers due to the strict networking requirement between resource pools, different logical pairs can be freely hosted in different data centers, and each data center is organized in a form of 3 local resource pools. This is what we refer to as split according to virtual peers. The blockchain world state has been implemented using an on-disk key-value store in the generic XOV architecture. In FlexChain, each peer's copy of the world state must span the local cache on compute nodes, the remote memory pool, and the remote storage pool. The world state is primarily stored in remote memory, which is slower than the local cache, but much faster than remote storage. Although users can scale up remote memory regardless of compute resources, the expense of using DRAM is still higher than that of using secondary storage, such as these disks. For that reason, FlexChain allows users to set a limit on the remote memory size according to their own budget. Once approaching this limit, some core world state will be evicted from the remote memory to remote storage in order to make room for some hot states that are newly written. More importantly, this step is necessary to store the world state in remote precision storage in order to achieve fast recovery when the memory node fails. The details on how to read, write, and evict buffers can be found in our paper. As FlexChain dynamically scales up CPU cores and remote memory, the execution phase and the endorsement policy evaluation are no longer the bottleneck. However, the validation manager still processes transactions within a block sequentially. And due to the high latency of remote memory accesses, this validation phase further becomes the bottleneck of the entire system. To maximize the end-to-end throughput of FlexChain, we leverage dependency graphs to fully parallelize validation. In other words, for transactions with no data dependencies, we can carry out the validation phase in parallel, including V2 and V3 stages, which represents the complete check and world state update. We implemented FlexChain by using libID verbs for all RDMA communications, and we use DevilDB on the remote storage servers. We run a disaggregation testbed on 20 bare metal machines on Cloud Lab and use effective throughput as the main metric. In the figures below, we plot how FlexChain throughput changes with the number of CPU cores per peer and the available remote RAM per peer. The left figure includes the result for both sequential and parallel validation. For compute-intensive smart contract, FlexChain can scale up compute resources to achieve better performance while leaving the amount of provisioned RAM unchanged. This boosts throughput from 566 transactions per second to around 4,000 transactions per second. For data-intensive smart contracts, FlexChain can scale up memory nodes and use remote memory to replace more expensive disk swapping operations. FlexChain achieves 140 times speed up when we increase remote memory from 1 gig to 50 gig. One key operational benefit of disaggregation is decoupling compute and memory resources. This can promote efficient resource utilization. We now run a mixture of smart contracts in 3 blockchain channels or instances. We have one compute-intensive contract, one memory-intensive contract, and one contract that is both compute-intensive and memory-intensive. We compare FlexChain with monolithic blockchain servers. FlexChain can save 48 cores and 192 gig RAM while achieving the same aggregated throughput. Now we compare FlexChain with the generic XOV blockchain deployed on monolithic servers. In the figure below, L represents local memory, R represents remote memory, so the blue bar represents FlexChain. Since M stands for main memory, the red bars represent generic XOV. When moving the same amount of RAM from main memory to remote memory, FlexChain has at most 12.8% throughput reduction and an overhead of disaggregation. When keeping local memory at 4 gig and increasing remote memory to 10 gig, FlexChain significantly outperforms generic XOV. Note this is the scenario where FlexChain is provisioned with extra remote memory, and it is quite straightforward to do so because memory pooling. Under another workload, without this extra remote memory, FlexChain also outperforms generic XOV for up to 30%. It is due to FlexChain's better buffer eviction mechanism, and more details can also be found in our paper. This concludes my presentation today. Thank you for listening.